So I want to go over the concept of work and the work energy theorems. In an introductory physics course, you'll learn how to solve motion problems by using your equations of motion. And you might be familiar with these types of problems. For example, throwing a ball into the air and trying to calculate the final velocity at some time. Or you throw a football at some angle at this trajectory and you need to find the distance it travels at this particular moment in time, or find its final velocity at this time, or calculate the initial velocity or the acceleration at this point in time. The types of problems for these are endless. And you'll use these equations of motion, which you might be familiar with. Your displacement is equal to your initial velocity times the time, plus 1/2 at squared. These are all vectors, so you put this symbol above it, meaning it can be in any direction. And here's another equation, your final velocity, or maybe you'll see it as your velocity at some time t, is equal to your initial velocity plus at. And you use these equations of motion when you're dealing with linear forces and acceleration is constant. Is constant. And this is an important factor for these types of equations. The reason for this is because acceleration is constant, meaning your acceleration isn't changing, it isn't like getting smaller as time goes on, and it isn't going up and down, left and right, and so forth. Pretty much if you were to graph it, your acceleration is either going like that, or it's going like this, and so forth, you know. But what happens if the acceleration is not constant? Well, what if, for example, we're trying to do this type of motion problem? Let's say you have this windy hill right here. And you have this crate at the top, like this box. And you push it down, and it starts sliding down the hill, this wavy, bumpy hill. Now, it's possible to utilize these types of equations, but you'd have to calculate you'd have to calculate at every single point where your acceleration changes. And that can range from a few changes of acceleration to hundreds of thousands of changes in acceleration. And using the equations of motion right here is impractical, and we can use a better method. And this is where work and the work energy theorems comes into play. And we use the work and work energy theorems whenever our acceleration is not constant, if it's always changing. So let's work with a question like this. We have a block on this plane right here. And it's sliding down. Let's say this is at a height of 3 meters. This is at 4 meters. And right here I'll draw 5 meters. So the question I pose, what is the final velocity? Now, we might be a little bit hesitant and a little bit nerve-wracked to solve this type of question, but you might say like, well, I'm not given a mass, I'm not even given an initial velocity. How am I supposed to find the final velocity in this case? Let me walk you through on how this works. Let's start off by defining what work is. Work is a force times your displacement value times the cosine of an angle, and that angle is between your force vector and your displacement vector. This applies only to the angle portion. Keep that in mind. It's very important. So, how can we use work to solve this kind of equation? What we're going to do here first is label the forces acting on the system. That's normally how I usually solve these types of questions. I like to draw out the diagram and I like to label my forces. So let's take a look here. We have a normal force acting up here. We also have, let me draw that in black. We also have the force of gravity. I'm just going to write this as mg because the force of gravity is mass times gravity. And in this case, I'm going to omit friction, so there's no friction in this problem here. Now, the next step of solving questions and using the work or the work method or the work energy theorems is to ask yourself, are my forces conservative or are my forces non-conservative? I need to write down all of my conservative and non-conservative forces. So right here, I'll just write a letter C to represent my conservative forces, and NC to represent my non-conservative forces. Conservative forces, your two basic ones are a spring force, and gravity. Those are your two conservative forces, the two basic ones. There are more, but that's what we'll stick to in this case. And non-conservative forces are any other force that is not a spring force or a gravitate or the force of gravity. Now let's go ahead and label what our conservative forces are. In this scenario, we have the force of gravity. That is a conservative force, and the normal force, or F sub n, that is categorized as a non-conservative force. So, recapping real quick, first we draw our free body diagrams, figure out what our forces are. Then the next step is to identify which forces are conservative and non-conservative. The next thing we have to do is ask ourselves, do the non-conservative forces, are they doing any work? We have to look at each and every one if they're doing any work. Now I'm going to write down again the work equation. Now, we said that the normal force is a non-conservative force, but let's focus our attention here for a moment and think of if it's doing any work. right here? Well, we know that there's a force done by the non-conservative force. We know the distance it travels because it'll travel down 5 meters right here. And the angle in this case is 90 degrees. Because if you take a look here, our normal force is pointed this way, and the displacement is going that way. So if we connect these for a moment, the red symbolizes my displacement vector, and the black symbolizes my normal force. You can see here, it forms a right angle of 90 degrees, and the cosine of 90 degrees is 0. So work by the normal force is 0. And this is what I mean by it does no work if you get a value of 0. And pay attention again how I took the angle between the force and my displacement vector. It's very important you do that, otherwise it'll skew your answers quite a bit. So we know that the work done by the non-conservative forces is 0. And what's really cool about this is now we can jump into our work energy theorems. And I will write all of them down right here. So we have the work, the net work, which is equal to delta KE, and our work done by our non-conservative forces, which is delta E. And don't worry, I'll explain what delta E means in a minute. And finally, we have our work done by our conservative forces, which is negative delta PE. Now, for a lot of these work energy problems, it's probably best to utilize the second equation right here. Now, what we're going to do, I will erase these for a moment, is we're going to start solving the question here. But before we do that, let's identify what I mean by delta E. Delta E is simply the mechanical energy. And mechanical energy involves all of your energies in this case. In this system, we're using the change in potential energy, gravitational potential energy, plus the change in kinetic energy. If this system had a spring involved, you would add on the change in spring potential energy. If this had heat, you would take the change in heat. It goes on and on. In this case, we're only limited to gravitational potential energy and kinetic energy. Now, since that is what delta E is equal to, let's go back to our work energy theorem. So we said our work energy theorem for the non-conservative forces is our delta E value. So let's take this force and plug it in here. We said that the value would be 0 in this case. We know that the non-conservative force here is going to equal 0. So what we can do now is we can write this whole equation out. So to clarify once more, I took the work energy theorem equation and I took the value that I know for the non-conservative force and I set them equal to 0 in this situation. And now what I'm going to do is I'm going to write everything out. I'm going to write delta PE plus delta KE is equal to 0. Now let's analyze and see if we can cancel out anything here. Is the kinetic energy changing? Yes, it is, because you start off at this initial velocity of 0, because it started from rest. And our potential energy, it is changing because this height value, as the block goes down, the height becomes smaller and smaller, eventually becoming 0. So nothing is going to cancel out here, so we can't cancel anything out. So what we have to do now is write everything out. So we have our mgh final plus our 1/2 mv final squared, and then we'll subtract that away from our mgh initial plus 1/2 mv initial squared, and all of this equals 0. And because it equals 0, I can take this term and move it to the other side of the equation, and that's what I'm going to do here. So they equal each other in this situation. Now what we have to do is start canceling and plugging in our known values. Take a look at this here. The mass is on both sides of the equation, so we can cancel out the mass. This is why I did not give the mass as a detail for this equation, or the question, because it's going to cancel out. So this means I can take any sized block, small in mass or large in mass, and it's going to travel at the same velocity at the end. Now keep in mind there are other factors like friction, air resistance, and everything else that will affect this. So this is more theoretical, in case that none of it was making any sense. Now we have to go ahead and solve for the rest here. And I'm going to clean everything up right about here. We have ourselves the value of g. We know what our final height is going to be. In this case, it will be 0, because as it falls all the way down, what happens to the height? You start off at 3 meters, but at this point right here where the block will end up at, our height is 0 because this is at ground level. At ground level, there's no height, and that's how we'll define it. You choose to define the point where h is equal to 0. Right here where I'm making this big black dot, that's where it's 0. So in this case, I can cancel out this entire term right here. This becomes 0. Also, the initial velocity was 0, though I didn't write the detail, and I apologize for that. It's starting off at rest, so you can just cancel this entire term right here. And now you're left with, I will write it in red up here, apologize for the mess, 1/2 v final squared is equal to g times your initial height. And now we want to solve for our final velocity. Let's rewrite it as this equation. And what I did here is I just did some algebra, that way I can get it to look like that. I just multiplied 2 on both sides, take the square root, and should be a little straightforward there. And lastly, plug in your values. So you have 2. I like to use 10 meters per second squared for my g value for gravity. However, you could use 9.8 meters per second squared. It depends on what is expected or what is required. In this case, I'll just use 10 for simplicity. And my initial height, take a look at this right here. We start off at 3 meters. So multiply that by 3. So my entire answer is the square root of 600 meters per second. And if you punch that out into a calculator, you'll get some value for that. And that is a brief introduction to work and the work energy theorems. I thought I'd go over that since I don't see a lot of work energy theorems, especially something called like the work done by the non-conservative forces and the work done by conservative forces. I've seen the net work done on other videos on YouTube, but I figured I'd go ahead and introduce this as well. If this is any way confusing, go back and try looking at the video again, and maybe I'll even post another video clarifying this if it's a little too confusing. I hope this helps, and these types of problems are not too difficult. You just have to think it through just a little bit. Always start off by drawing your forces, and that seems to really help for most of the problems. Thank you for watching.